Fun. Okay, I hope folks online can hear us okay. Welcome to another episode of GPU Mode. Today, I'm really thrilled to have like three of my colleagues. Like we're going to be giving a sort of a special lecture on Helion. So just like to quickly introduce the speakers, like a lot of the people here were like some of the main inventors of like Torch Compile. Like Jason was like sort of the primary author of the module. Oguz did a lot of like interesting work on like reducing like compile times, and if you want to complain more about compile times, you should reach out to Oguz. And Will did a lot of the early work with like making sure the compiler works well with distributed, and has been kind of like a long-term PyTorch maintainer as well. So they're some of my most knowledgeable colleagues, so please ask them hard questions. But without further ado, I think today what they really wanted to talk about was Helion, which is their new DSL for kernel authoring. So folks, yeah, please take it from here.
Great, thanks. So I'll start off with some slides to basically go over the ideas in Helion, and then I'll hand it off to Oz and Will, who will go through some more hands-on examples. So start off with some motivation. Okay, why do we need a new DSL? And sort of the way to think about Helion is it's sort of at a higher level of abstraction than a lot of existing DSLs like Triton, but a lower level of abstraction than PyTorch. And really the moment that sort of motivated it for me was we kept on getting asked from users of Torch Compile to get more control. Like people wanted control over the exact kernels that get generated. And for that, you really need a DSL. But you need it. You sort of would want a DSL that's at a closer level of abstraction to PyTorch that sort of lets you use a lot of the concepts that you already know from PyTorch without needing to worry about low-level details of the specific kernel. And so a big differentiator and sort of what makes Helion able to get performance competitive with much lower-level DSLs is the use of an autotuner. And so the idea is that Helion is sort of integrated into the language, has a very sophisticated autotuner, which searches thousands of different different Triton kernels, which are generated from a single Helion kernel. So basically, the search space defined by Helion kernel is a superset of the search space that you get from sort of a single Triton kernel implementation. And this search has a bunch of advantages. One big advantage is it saves human time. Basically, rather than needing to spend human effort to try hundreds of different ways of implementing a kernel, you can let the autotuner do that and basically trade sort of human effort for machine effort. And then the other big advantage is hardware portability. So often what we see for kernels written in lower level languages is every time a new hardware generation comes out, you need to rewrite your kernels but with a higher level language combined with an autotuner, you can just retune for each hardware generation and get much better portability between hardwares. So let's go through an example of what a matrix multiply looks like in Helion. Are people still seeing the old slide? I'm not seeing it.
Right now, we're seeing autotuning as a slide.
Okay, I advanced my slides. Oh, there it goes. There's
okay, yes, it worked.
Okay, so let's go through a matrix multiply example in Helion. This is what matrix multiply looks like. Inside the Helion kernel, you basically have two main parts. So you have this outer part of the kernel, which is basically just regular PyTorch code. You use it to allocate your output tensors. And then you have this inner part of the kernel, and this inner part of the kernel gets compiled down into a Triton kernel. It'll be a single kernel, sort of guaranteed. And what you have here is you have this outer hl.tile loop. This outer hl.tile loop basically becomes the launch grid of your kernel. Then within this hl.tile loop, you can use PyTorch operations like add mm here. And you're basically operating on tiles. And so you could sort of think of it as PyTorch with tiles. And it looks like there's a big delay in my slides, because let me try resharing.
We can also let's give this a few more shots, and if we keep running into technical issues, we can try something else.
Sure. Let's try that. Okay. Yeah. So there are a bunch of language constructs in Helion. So the main one is this hl.tile construct, and this hl.tile construct subdivides the iteration space of a given size into tiles. And the exact details of how that space is subdivided is up to the autotuner. So the autotuner is picking tile sizes, it's picking iteration orders. It can do swizzling to change and flattening to change iteration orders. Then within the hl.tile loops, standard PyTorch operations can be used. So if you know PyTorch, you already know most of Helion. And it also supports stuff like control flow and other things. So now I'm going to go over the configuration space. And I think going over the configuration space is a good way to get sort of a tour of the language, because you can see sort of how the Helion is lowering different things and sort of what they correspond to. So the first part of the configuration space I'm going to go over is the indexing mode. So in Triton on the right, you can see there's actually 3 different ways to write indexing. You can do sort of pointer math. You can do block pointers, which is a more structured way of doing it, and then tensor descriptor, which is similar to block pointers, but works on the latest NVIDIA hardware. And in Helion, you just write regular sort of PyTorch style indexing with tiles as arguments, where sort of the tile is specifying a block. It came from hl.tile. And the autotuner can auto-tune between all 3 of these. And what we find is that sometimes one is faster than the other. Like we've seen cases where tensor descriptors are faster for big inputs, and then pointer indexing is faster for smaller inputs. And the autotuner can select this for you, which saves a lot of work, because it can be pretty tedious to rewrite your kernel to do different types of indexing. The next choice I'm going to talk about is block sizes. So as I said before, when you write an hl.tile loop like this, you're implicitly defining some block sizes. And the corresponding Triton code for this is on the right, where you see there's a lot of boilerplate to sort of thread block sizes around. You need to do some math to compute grid sizes, and so on. And all this sort of boilerplate is removed in Helion, and you just write sort of this higher level concept. And by expressing the tiling in a higher level way, it also allows Helion to do more sophisticated things, like if you set the config flatten loops equals true, then we basically take those 2 block sizes that I had in the previous slide, and you flatten them into a single block size, basically turning your 2D iteration space into a 1D iteration space. And this allows searching over things where it would be very tedious to do this at the Triton level. The next thing I'm going to talk about is reduction ruling. So if you write a reduction like this in Helion, where you're basically reducing the rows of a 2D tensor, you can express this sort of naively, sort of in a straightforward way, where you basically load the entire row into a tile in the output language, and you do the sum here. This has the problem that if your sizes are very large, you'll end up running out of registers, and if it's even larger, it'll just fail to run, because basically the single row won't fit in an SM of your program. And so the way to handle this is to do a reduction loop, where you could basically have an accumulator. You can iterate your accumulator over your data, and then that accumulator has a block size, so it sort of introduces a search space, and Helion will automatically convert between these 2 different ways of writing reductions. Next is the PID types. So this is the program IDs. There's a lot of different ways of expressing program IDs. You can either do a 1-dimensional launch grid, a 2-dimensional launch grid, or there's a number of different ways of doing persistent launch grids, grids, where persistent launch grids basically mean that you run one CUDA program per SM, and then that CUDA program is going to iterate over virtual program IDs, which allows pipelining across CUDA programs. And we can auto-tune this as well. We can auto-tune optimizations over grouping and reordering. So we can reorder loops, which is just swapping the loops around, or we can do sort of subtiling of the iteration space, which can help with cache reuse. And we can do this automatically. There's lots of configuration flags that try and exposes. There's, for example, num stages, warp specialization, num warps, etc. And we basically auto-tune those as well. These are basically like passed through to the Helion autotuner. And then another thing, the final thing I'll talk about sort of in this section is automatic masking. And so masking can be tricky to get right, and Helion automates a lot of this for you, and will also optimize it away if you're in static shapes mode. So next I'm going to talk about the
Actually, Jason, mind if I ask you a few questions before you go to auto-tuning? So I just want to as you're sort of going through this, like my first thought was like, oh yeah, like this is basically Trident with like some of the annoying parts sort of like smoothed over or auto-tuned over. And so then, well, how do you think about like the identity of the language? Like basically as the language evolves, like what are features that you would expect to see sort of in Trident versus in Helion? How do you sort of make sure that it just doesn't become like sort of like a bit of a random repo? Yeah, like any thoughts on the just overall direction?
Yeah, I mean, the main direction is to try to build something a lot closer to PyTorch. Things that I definitely wouldn't want to see sort of leak too much into the language would be hardware specific details, because a big motivation here is having a language that works on lots of different types of hardware, and so you need to sort of keep the concepts high enough level that they work across many different types of hardwares. Also, I think having an integrated autotuner in the language allows you to do a lot of things which aren't really possible in languages without an integrated autotuner. And so I think like the autotuning part of Helion is they're pretty core to the identity of the language.
And so related to this, like a lot of your colleagues sort of building kernel DSLs have taken the opposite, but where they're like, oh, like Blackwell made everything too hard. You need to call the low-level intrinsics. It's very hard to build like sort of generic primitives. Therefore, we need a DSL per like new hardware architecture, at least have the language change such that it's indistinguishable from the one from previous generations. Like, what's your thinking on like taking the opposite bet here?
Yeah, I think we definitely need both, right? Like where you look at a language like Python, which is very high level, and Python's incredibly popular. Lots of people want to use Python. But if you want the very fastest performance, well, you probably should be writing either C++ or inline assembly or something like that. And as someone who I love both languages, I love both Python and C++. I wouldn't want to go without either. Like there's sometimes I want to go super low level, but like for my everyday programming, it's really tedious to write C++ with inline assembly. It's a lot of work. And so what I'd say is you would sort of sit into that same thing where like most of the time I'm writing Python, but when Python when I want like to go really low level and like sort of really try to squeeze the very last dropout or something, I'll be writing that inline assembly as well. And so I think they complement each other. It's something where my hope would be that the Helion autotuner makes Helion fast enough that people don't need to go down to like inline PTX in their or low level CUDA. But those options are there, and I think it's good that those options are there.
Perhaps it's also like valuable to add that like there's like some sort of like a chart where like amount of effort you put in versus amount of performance you get. And like I think there's like already like some charts flowing in on the internet about like with Triton, with Qt DSL, with Helion, or like with writing like Cutlass, Cubase, whatever. Like the Helion just makes the amount of effort to get good performance very low. And then if you want to get like the peak performance, perhaps you might need to pick a more hardware specific language.
I think, yeah, I know which picture you're referring to. I'll put it in chat because people keep referring to it. I think TreeDAO had
Yeah,
one that was basically referring to how cute DSL bends the curve a bit. But yeah, like I think maybe different DSLs will sort of say similar things. But yeah, sorry, yeah, we can keep going. I think this digression. I've interrupted you for too long.
Yeah, no worries. All right, so now we're talking about auto-tuning. Auto-tuning takes about 20 minutes to search 1,200 candidate kernels.
Actually, Jason, sorry for interrupting again, because there was a question that I think was very directed at you. Were there any inspiration from Halide here? Like I think, yeah, like I think Torch Compile was, but I'm not sure Helion did. So any comments on that?
Yeah, I mean, definitely, like I took a lot of inspiration from the way Halide works, and you could sort of view, like Halide really pioneered the idea of sort of splitting out your semantics language versus your sort of scheduling language, and you could view the sort of the Helion language as like the semantics language, and the auto-tune configuration as the scheduling language, and so that definitely sort of takes. And then also the auto-tuning, combining it with an auto-tuner to auto-generate the schedule, which the original Halide didn't really do, but sort of follow-up work to Halide did a lot of it. So that's definitely a source of inspiration.
All right. Oh, okay. Auto-tuning.
Yeah, and one of my very early projects in grad school was actually one of the first auto-tuners for Halide. So I know a lot about auto-tuning Halide as well.
Yeah, I mean, I'm sorry. I really want you to keep going, but people are asking questions, so I figure we can just go through them. So someone's asking. So Stephen is asking: Is this like giving another abstraction between Torch, Inductor, and Trident? And does it provide a lower level abstraction for better optimization, like Gluon as well?
Yeah, so it is a lower level abstraction than Torch Compile. So it gives you a lot more control. Like within Torch Compile, you sort of just give PyTorch your Torch program, and then Torch Compile will figure out, okay, what gets fused with what. How many kernels do you have? It has sort of a lot of optimization there. Within Helion, you have explicit control over exactly what goes into the kernel, and so it provides much lower level of control. There are escape hatches in Helion that allow you to go level. Like you can insert inline PTX into Helion, you can insert inline Trident into Helion, but it's definitely a case where it's not designed to be sort of the equivalent of the lowest level language. It's designed to be a very high level language that gives you performance through auto-tuning. So hopefully the auto-tuner can search over the types of choices that you'd be searching of, that you'd be implementing manually in a low level language. But we're trying to basically automate a lot of this for you.
All right. I see one more question from Matt. I think we'll pause after that question and then rebatch the questions later. So Matt's asking, and let me know, Jason, if you have a later slide on this, but have you considered parallelization strategies as part of this auto-tuning process?
You mean parallelization during of the auto-tuning process, like trying multiple things at once, or parallelization of the output code?
So sorry, I actually mean, like, I think Matt means parallelization of like distributed parallelism, as in like things like auto-tuning, making something like work over that, like DP, PP, CP, TP, etc. This is what they're referring to. The composition with distributed.
Yeah, so there are some examples of in the Helion repo of mixed comms compute kernels. So you could do things like try to overlap your communication and computation. That works still pretty early. Because Helion is a kernel authoring language, sort of definitionally a kernel runs on exactly one GPU. Like the scope of a kernel is confined to a single GPU. But a Helion kernel can include communication to other GPUs, and so you can basically like implement sort of parallelism there. But that's sort of done at a higher level than at the kernel level.
All right, I think we can finally get to auto-tuning. Maybe we'll see.
All right. Yeah, so the Autotuner, today we have a few different algorithms. These algorithms are still pretty simple algorithms, but we're really excited about in the future, looking at things like LLM guided searches, reinforcement learning, shared performance databases where you could try to predict stuff. But right now we basically have a pretty straightforward auto-tuning algorithm. So I'll go through how this auto-tuning algorithm works. You start off with your initial population where you just randomly pick 100 configurations. You then select the top 5 fastest configurations. Then on each of those fastest configurations, you hill climb to a local minimum, and then you take the fastest of the local minimums that you found. And empirically, this works pretty well. We found that the search spaces for these kernels is pretty regular, so we're able to get pretty good performance from this. But we'd love for this algorithm to be faster. This is pretty computationally expensive, and for more complex kernels, it's quite possible that more sophisticated algorithms would be required. So how do you deploy a configuration? So we have the most straightforward way, if you just want one configuration for all shapes, is you can just take the output of the Autotuner. The Autotuner will print out the config that was fastest. This is what a configuration looks like. And you can just copy and paste it into your code, check it in, and then in subsequent runs, it'll just use this configuration without any Autotuning. In some cases, you might want multiple configurations. Like, for example, if you have different shapes that you're dealing with, in this example, you have a small shape and a large shape, you can run the Autotuner for both the small and large shapes. And then you can specify 2 different configurations. You can say configs equals first config, a second config. And what will happen is every time you call a kernel, it'll if it's a unique shape, if it's never seen that shape before, it'll try both of the configurations and pick whichever one's fastest, and then cache that result, which works pretty well in a lot of environments. And then if you want to go even more advanced, you can manually route to which configuration you want. So in this case, I've ahead of time compiled the 2 configurations to a small runner and a large runner, and then I wrote just sort of a simple routing function, which says, okay, if the numl is small, then use this one, otherwise use the other one. So now I'll talk about some performance numbers. So the first case study I'm going to show is a comparison to Qt DSL and Quack on RMS norm backwards. There was a post a while ago that sort of showed some of these numbers here. And so we tried to reproduce them with Helion included. And what you see here is torch compile is doing really well for some smaller sizes. Quack is doing really well for the largest sizes. But you can see that Helion and then also sort of the fused white trident equivalent of what Helion is doing tend to do really well for all shapes. So you get sort of better performance portability across different sizes. So these are still some work in progress numbers.
Jason, what GPU are those numbers on?
These are H100.
Cool, thank you.
So here's some B200 speedups over where we're showing the Helion speedup, the torch compile speedup, and then the handwritten trident speedup. Most of these handwritten trident kernels are coming from Liger, which is a repository of handwritten trident kernels. And what we can see is that for most kernels, the Helion one is the fastest with a geomean of 3.2 times faster than in eager mode PyTorch. We can see that we're almost twice as fast as handwritten Trident. This is mainly because the Autotuner is able to tune the Trident code much better and sort of squeeze more performance out of the Trident compiler than you would get through manually writing Trident code. Here's some results on AMD. The AMD numbers show a pretty similar story to the B200 numbers, where Helion's fastest in most cases. Again, we sort of see the same pattern where the autotuner is able to give you robust performance across a large number of shapes. So coming towards the end, I'm just going to have one slide on how the internals of Helion work. So this is sort of a diagram of the compiler. Because we're a Python embedded DSL, we start off with a Python AST, the abstract syntax tree. We first annotate this AST with types and metadata. We then convert it to a number of FX graphs, one FX graph per basic block. Every node in this FX graph has an inductor IR attached to it. So Helion basically is reusing the inductor compiler to generate a lot of its output code. We have compiler passes that operate on these IRs. And then finally, we have CodeGen. We only incorporate the configuration that's the Autotuner came up with during CodeGen, so that basically everything to the left of this can just be run once, and then everything to the right is rerun every time during Autotuning. And then we generate a Triton code as an output, and for the wrapper code that basically calls the kernel, we're using an AST rewrite. Basically, change that for loop into a kernel call. And then I'd encourage everyone to try Helion today. Definitely, we'd love some feedback. Early feedback helps shape the language, and then contributions are welcome. We'd love for people to submit PRs and have some improvements. And we're releasing a beta on Monday.
Sweet, awesome. Thank you, Jason. I guess before we transition, I had a couple of questions. So when you were showing like the B200 numbers, do you have like sort of a qualitative sense of like what was it that Helion did really well that like wasn't like what was it that Helion did really well in sort of specific use cases where the performance differences were quite big that wouldn't have been as easy to express in the sort of existing alternatives like compile or just raw Triton?
Yeah, I think that, like, I went over all the sort of things that it's searching over. I don't have the exact details of like, oh, for this kernel it did this and this and this, but that type of case study to dig in a little deeper would be I agree, it would be super interesting. But I don't have it here.
Yeah, it would be a good first contribution too, I think, if anyone in chat is interested. So related to so actually unrelated to this. So typically for auto tuning, when you're first picking does it typically work by random initialization in the beginning?
Yes, it starts off by random initialization.
Completely random. Okay. Last question. In your diagram, like the architecture diagram, what's a basic block?
Oh, so a basic block is a concept in compilers where the idea is that it's a sequence of code that has no control flow in it. So if you have like an if statement, then you'd have one basic block before the if statement, and then two basic blocks depending on which side of the if you go down. Similarly, for a loop, you'd have sort of a basic block from the body of the loop, and so on. So it's easier for compilers to work. Control flow is like a tricky thing to compile. And so often sort of compilers work by like splitting things into basic blocks which don't have any control flow, and then you have like one compiler process for the basic blocks, then other things that sort of cross basic block boundaries.
Okay, sounds good. Thank you, Jason. I think we can transition to the next part, which is like I believe like Oguz slides. So let me just remove this. All right, yes, Oguz, please take it from here.
Okay. Hello. So I'm Oguz. I have also been working on the Torch compiler and also Helion. So today I'm going to be talking a bit about like the documentation, how to like get started with Helion, and then I'm going to walk through a few simpler kernel examples, and then compare a few like more advanced techniques. And then after we'll take over with like more interesting kernels. So the first way to get to Helion is like if you go to helionlang.com, this is the main website we have for Helion documentation. This will just explain a lot of the topics that Jason talked about in the presentation in more detail with like examples that you can try out yourself. And the easiest way to get started with Helion is by just going to doing pip install Helion. In addition to this, you will have to also install the PyTorch 2.9 and Triton 3.5. The PyTorch 2.9 was released, I think, yesterday or the day before. So you can just download it from pip, and then if you do pip install Helion, you will get the most recent version of Helion. On Monday, we will release 0.2, which we will consider to be the stable. Like, it's already stable right now, but 0.2 will be the official beta version that we will release on Monday. Okay, now with that out of the way, the other interesting part here, the website, is the documentation. So in the docs, we can actually just, sorry, that was an API reference. So in the API reference page, you can look at our individual language semantics. Like, for example, we can read about like TL.tile. Generally, when we refer to TL, we mean HL. When we refer to HL, we mean Helion language. And like, you can read about how tile works, what arguments it takes, like how to pass a block size, begin, and other arguments as well. And you can click on various other language constructs here to read. It's just like very similar to how Helion works. Sorry, how the Triton works. So now let's take a look at the examples. So this is I hope this is big enough. So this is the add kernel. This is also on our website. If you go to Helion examples add, you can see this. So add kernel is like one of the simplest kernels. All you do is you take two tensors and then you sum them up. As Jason mentioned, the kernel has two distinct components. There's the device side and there's the host side. So everything that you write outside of this for HL tile loop is the host side, where you can perform any torch operation you want, or you can perform any other Pythonic operations you want. All the code in the host side will be executed in the eager environment. There will be no compilation. And then this host code can exist before the HL tile loop and also after the HL tile loop. And inside the HL tile loop is what we call the device region, where Helion will compile into a Triton kernel. One super important abstraction about, abstraction about a Helion kernel is that we're guaranteed to convert a single Helion kernel into a single Triton kernel. There will never be a case where we will end up with multiple kernels. Everything inside the device region will be converted into one fused kernel. So with this add kernel, we broadcast the sizes, we create an empty tensor for our output, and then we just tile over the entire size, and then we just add it. And then when you auto-tune it, you can identify different strategies where we will emit different versions of Triton code, depending on like what are the most ideal settings for your shape size. So moving on, let's take a look at matrix multiplication. And one interesting thing we'll talk about here is this lambda we're passing into the matrix multiplication for epilogue. So in this case, Helion kernels are able to take a lambda function that can be executed inside the device region to perform some operations. Suppose in this case we pass two matrices, and then in the epilogue we pass an activation function. Say we pass a relu. So what we do here is we again create an empty tensor, and then we're now doing tiling over using an accumulator. And then we accumulate over the subtile, and then we eventually write this result into the output tensor after this accumulated result. But before we write it, we actually call our epilogue. And if in this epilogue we pass the relu, the relu activation function as I mentioned earlier, then the output Triton kernel will also emit the relu in the Triton format. So moving forwards, another interesting technique is sometimes you need to pass two different tensors, but you don't actually want to operate over the entirety of the tensor, but you want to do some masking. So let's take a look at this kernel that concatenates two two-dimensional tensors on a single dimension. So you pass your two tensors, and then you again create your output tensor. But in this case, we want to create an output tensor that is the summation of both of their lengths in the second axis. And then the interesting part here is that now that we're tiling over the entirety of the output tensor, we can't just access the elements of the first and second tensor with the same tile 0 and tile 1, because that would be out of bounds. So when we're loading the first and second tensors here, we can pass an extra mask argument that will allow us to mask, like only access the correct parts of the tensor and then zero out the rest of it. And then we can use a simple torchware operation in order to write it into the final tensor. Is there a question? Something is beeping on my end. I can't see. Okay, I will continue. So now we're going to look at RMS norm. So the RMS norm is a fairly straightforward normalization function where you do the root mean and square operation, and this is just you take a value, you take your tensor, you divide it by the square mean, the square root of the mean squares. So in this kernel, we're going to take a look at how to write a very straightforward RMS norm implementation, and then we're going to look at writing a more advanced version of it. Advanced version doesn't necessarily mean it is more performant. In fact, in most cases, Helion is able to generate the exact same advanced version through autotuning. But I want to use this as an opportunity to talk about some of the more interesting features. But before then, let's keep going with the regular RMS norm. So with the normal RMS norm, you take your inputs, you take your input tensor, you take your weights, you take your epsilon value, and then again you create your output, and then you tile over the input. Sorry, you tile over the region, and then if you notice here, we're using torch mean and then torch reverse square. These operations are all they don't do any reductions. They I guess they do a reduction over the whole line. So in some cases, this might be not as efficient because you will have to load the entire line. And again, as I mentioned, the Helion autotuner can do these reductions for you so that they are they're not loading the entire line and they're loading smaller components. So one interesting way of rewriting this kernel would be to actually do these reductions yourself. And so if you look at this kernel, we have this function called HL register block size. What this does is that if you want to have multiple inner reductions in your kernel, but you want to ensure that these inner tiles are both over the same block size, then you can register a block size ahead of time, and then this will indicate to our autotuner that whenever this block size is used, we need to make sure that both of the tiles are using the same block size. This is one of the more interesting ways of, writing a kernel with our own reductions. If we go back to the documentation I mentioned earlier, you can search for the register block size, and this will talk about how this function is being used. So as we mentioned here in the documentation, this is really important when you want to share the block size. So going back to the kernel, another interesting thing here is the eviction policy decisions. In a more naive implementation, even though you have to, where is this? So in this case, we have to take the mean over the squares and then later do a division of this value over these mean, which means that we will access this x value, we will access the value of the x multiple times. So we don't actually want this to get evicted right away. Whereas with weights, we are only using it once, so we can, after we use it, we can directly evict it. So HL load operation also takes an eviction policy argument, exactly the same way the Triton would take, and then we can ahead of time explain that this to our autotuner. To our autotuner that this argument, if we actually want to evict last, because X will get reused again. And then our next use of X, we know that this is the very last time we're using it, so we can evict this at this point. So this is a more advanced way of writing your Helion kernel, where you can actually control these reduction dimensions, and you can also control how you want these kernels to be evicted. And as I mentioned earlier, our autotuner will actually, in this very simple RMS norm case, or Autotuning will actually do these decisions for you, so you don't have to do it by hand. But in other cases where you want more explicit control over how your kernel is emitted, you can do these decisions yourself. I think this is everything I had.
Okay, I had a bunch of questions.
Okay.
So first one from chat is from Stephen, who's asking, like, how easy is it to capture Helion kernel from GUDA or HipGraph and then replay it later? Is there any issue like the typical kernel with dynamic parameter like sequence length with the Helion kernel?
So in general, CUDA should work with Helion kernels unless you're doing something that's not CUDA in the host code outside the kernel. If you do something like not CUDA by default, that will work, but most Helion kernels will work.
So and now more about like questions. I have a bunch of questions about like the programming experience of Helion. So like there's like one of the like a local favorite in GPU mode from torch compile is the torch logs equals output code. So you can just like look at code and mod it. Like, do you presumably have something similar where people can quickly understand, okay, like what the heck was auto-tuned over, or like what was actually the code that's running that people can take a look at and build intuition?
Let me actually really share that really quickly. So all of this is conveniently in our documentation page. Let me hide this. Okay, so if you go to Helion Lang, I believe we have a, okay. So there are multiple ways to do this. The simplest way, if you pass, is my screen big enough to be read on the stream?
It's okay. You could make it a bit bigger if that's okay.
Cool.
Yeah. That's
okay,
fine.
so we have a few environment variables, and I think there's actually a page in the wiki somewhere that explains all these environment variables. I cannot remember off the top of my head, but I know there's a chart. So settings for, if you scroll down on the first page, there's the settings of our development and debugging, which actually go over two very important examples. So first one is Helion print output code equal 1. What this does is that once Helion, like when Helion is running binds the kernel and generates Triton code, this outputs the Triton code we generated. It also outputs an easy way to create a repro. So in addition to the kernel itself and the host code that actually calls the kernel, we also emit a call function with input tensors that would be what's similar to what you would use. Like in some cases, you might need to modify this exact like the inputs in order to get the example you want. But it emits this like Helion print output code equal 1. Also gives you an easy way to emit just like something to repro with. The other interesting environment variable here is Helion autotune effort equals none. So when you're writing your kernel, you're still testing things. You don't want to wait 20 minutes to get an output, because like at this point you might not care about performance. You might just care about, does it work? Is it corrected? Like, is it good enough? So in this case, we have this Helion autotune effort equals none, which picks just the default configuration for autotuning, and it does not perform any autotune. We have two other options for its autotune configuration. I don't remember exactly where this was, but there's like a faster autotuning version that spends less time on autotuning, and it like finds a good enough result instead of the best result. But by default, we do the 20-minute autotune, as Jason mentioned earlier. One other debuggability, so like I guess like there are two other debuggability things. Another interesting feature is that we have Helion in, okay, it's not here. So we have Helion interpret equal 1, but this is another environment variable. What Helion interpret equal 1 does is that it, instead of running the kernel using the Triton backend, we actually convert the kernel into FX graphable code, and then we just run it using PyTorch eager. What this does is that in the HL tile loop, everything we have is what you would run over all the tiles anyway. So instead of doing tiling, we just run that device code over the entire kernel over the entire region using the interpreted eager version. And lastly, if you want to further debug your Helion kernel, we have similar to torch logs, we have 8 like Helion logs. And if you pass Helion logs equal all, or you can do like Helion log plus all, which enables a debugging level, this will emit a lot of internal diagnostics that can help you identify what's happening in your kernel. and we're happy to take more contributions to improve the user experience for kernel authoring and also kernel debugging. Like for us, the user experience is the utmost important thing when writing a Helion kernel.
So speaking of UX, then, like maybe people got used to it nowadays, but I remember in the early days of like Trident, like people were confused, like, oh, like, print statements don't seem to work, like breakpoints don't seem to work. There are certain things that need to be in the launcher code versus like the host code. In Yalza's case, it does seem like when I looked at the code, it did look like real PyTorch code. So I'm just trying to understand, like, is Helion actually just Python code, or is it like something else? Like, what's allowed versus not? I noticed one of your examples, you had an assert, for example, that seems to work just fine. So what should users expect to work versus not work inside the Helion.kernel decorator?
So as I mentioned earlier, like we have two sections of the code. We have the device and we have the host code. Both of these sections go through our own like type inference and type propagation algorithms. So technically, everything should work inside the host region of the code. There should be no limitations of what you can do, except like when you emit like a torch operation over like some tensor, we do emit a warning because like that would be executed using eager. So everything in the host code is going to be in eager, and you should be able to do everything. Then again, like there are probably some rough edges there since this is like we still have to run our type propagation, and there might be gaps in the type propagation. So we also welcome contributions and any like GitHub issues that you might run into there. But essentially, as a host region, you should be able to do anything you want. In the device region, this is the part like in the for loop, which is the device region. This is the part we emit a Triton kernel. In this kernel, there are some limitations. Like for example, if you have a print statement, we automatically convert that into TL print something. I forgot the exact TL version, but like we convert that to the TL version, and you're able to get you're able to print it with whatever functionality Triton has for printing. For breakpoints, I don't believe we have support for it in I guess I have never tried actually breakpoints. It is something that we can support again in the host region, but in the device region, that would not also be not supportable. I guess one other plug, if you use Helion, if you're into any problems, please go to the issues section and create a new issue with either bug report, feature request, or just anything you want, and we will take a look right away.
Okay. One more question. I think Stephen is asking this question, and I actually wanted to ask this as well. So I think this is good timing. So, like when you look at like a lot of like modern kernel code, so especially specifically in projects that are like mega kernel projects, like there's sort of like a lot of scheduling code in those kernels, like not just like how what the compute is done, but like how it's going to be executed and which resources and how to communicate between them. So how easy would it be to build something like a mega kernel in Helion? To do some of sort of like Mirage-like work, and would it be helpful, or is it solving like a problem at a different level of abstraction?
Yeah, I was thinking about that a little bit, where you can imagine. So currently, you can have multiple HL.tile loops in your kernel, and that basically becomes like a for each kernel, where basically all of the iterations run in parallel. But you can imagine adding something like a barrier operation, where the barrier operation basically says, okay, all the HL.tile loops before this need to run before all the HL.tile loops after that. And by adding sort of that type of construct to the language, you could have have a really easy way to write these sort of mega kernels, where you do sort of an entire model in a single kernel. So that's not implemented yet, but that's something that I was thinking about a bit. In terms of like when's that profitable? That's most profitable for very small sizes, where if you have a sort of full size model, like you're like Lava 80 plus, the kernels are big enough that the kernel launches sort of don't really matter. But if you have really small sort of kernels, then sort of these type of mega kernel strategies can be very profitable. And so that's something that we're interested in. We'd love contributions there. Hopefully we'll get to it, but it's not there yet.
Also, we didn't touch during the presentation, but currently Helion does support these like for each kernels, where you can have multiple top-level HL tile loops. The support is like there's like limitations in support, and this is something we're still working on. but it is like the for each tile is supported with multiple top level for like HL tiles.
Okay. I guess, Will, you're up next.
Yep, sounds good. Let me share my screen. Can you guys see it?
Yes, maybe just zoom in a tad more if you could.
Zoom in? Okay.
Yeah, thank you.
Okay, cool. Yeah, so I'm gonna quickly go through how to write a attention kernel in Helion. So to start, we're gonna review what the attention kernel is. So it's pretty easy to look up online. Attention kernel essentially is something like this, where we do a matrix multiply of Q and transpose of K, and then divide it by the head dimension, the square root of the head dimension, apply a softmax over this operation, and then do a matrix multiply with the V matrix. So if we express all of that in just pure PyTorch, that would look like this, which is pretty straightforward. And sometimes we want to maybe decompose the softmax to have like better numerics control. So we'll can have another version that looks like this, which does the QK matrix multiply and then do a decomposed softmax, which is like a bunch of like exponential and sum operation, and then do the final memo at the end. So when we want to write this kernel in Helion, so this is how the kernel looks like, which is like in the host code we do a bunch of like tensor setups and like reshaping to make sure we are processing with the right shape. And then this is the first HL tile that we encounter. So the key consideration when we write a Helion kernel is that for this kernel, what are the dimensions that we can parallelize over, and what are dimensions that we must sequentially execute? So for example, for the attention kernel, what happens is that only the softmax dimension, only the softmax operation needs to which is a reduction operation that needs to have a sequential operation over the n dimension. For the other dimensions, we can actually just like parallelize over them, the computation on them. So in the Helion kernel, what we do is that for the first HL tile, which maps to the Triton kernel launch grid, we will parallelize across the batch times number of heads dimension as well as the m dimension, and this will be our first HL tile loop. And then within the first HL tile loop, we need to do the softmax operation. So what we do is that we will do another HL tile inner loop within the outer loop over the n dimension, and then for each tile in this in the inner loop, we will go through the attention operations. We'll go through the Q and K matrix multiply. We'll go through softmax, and we'll go through the matrix multiply with matrix V, and then we update the running max logics for the softmax reduction. And then at the end, we finish off the softmax, and then we will save the output to the output tensor. So I would say that like the most important consideration when writing a Helion kernel is what dimensions to parallelize and what dimensions to sequentially execute. And then for the rest of the because like when writing Triton kernels, we always need to worry about like offsets when reading data and making sure the shapes align and things like that. Helion try to take away. Helion try to just like solve all the like those boring considerations and then leave the interesting consideration to the user, so that user can think at a high level, just think about what to parallelize versus what to sequentially execute. So we can actually use the Helion print output code environment variable that Uz just mentioned to see the output Triton kernel. Let's just run it here. So here, so starting from here, this is the Triton kernel that this Helion attention kernel generates. So we can see that within this Triton kernel, it's actually semantically is matching what the Helion kernel does, but just with a lot of boilerplate on how to compute offset indices, stuff like that. And then we can also see that the outermost HL.tile is converted into this like launcher with the grid size here. This is like parallelized over the product of this. And then you can see that when we run the Helion kernel, we automatically generates both the Triton launcher code and the Triton code itself, so that unlike Triton where you have to like write both a launcher and the Triton code itself, Helion just like handles it for you. And since with the event variable you can just generate the Triton kernel, it's pretty easy to debug when numerical issues happen, or like if output doesn't match the reference, it's pretty easy to tell what's going on. And I also want to show that sometimes, for example, if we are writing for like specific hardware like Blackwell, which is pretty new, and then maybe there are some optimizations that are not exposed in Triton yet, we can actually have very hardware-specific instructions used in Helion. For example, here we can like directly call some FMA operation, which is like actually I didn't have a definition here, but it essentially just calls the PTX inline PTX instruction within the Helion kernel, so we can support this kind of operations as well. Yeah, that's all I want to show for the attention kernel.
Thank you. Well, like a few questions. So like, how do you decide whether to sort of have a function that's mapping to PTX versus just like sort of like inline adding strings? I think Triton, for example, went for the choice of you can just like dump in PTX strings directly in your code. Does this is like a convenience thing for Autotuner, or is it just like a purely aesthetic difference?
We support the exact same thing in Helion. You can just dump inline PTX as a string. I think the implementation of that underscore FMA is just the same. It's just an inline PTX.
I will show the example. Just one second.
Yeah, I can also show maybe just pull up the code. Just quickly go over it. Yeah. Okay, here.
Okay, you found it.
Oh, I see.
Yeah.
I see. It's
Yeah.
literally I see it like a wrapper.
Literally, it's the same thing.
So Will, you mentioned something interesting in passing, which was that like one of the most important things in Helion is you need to have like an intuition for which dimensions you need to parallelize over versus which dimension you need to go over sequentially. Did you mind like elaborating on that like concept a bit more? Feel free to use a simpler example too, if like with attention this requires a bit more thought.
Yeah, so my understanding is that with Triton, what is parallelized over is always the launch grid. Like the launch grid, however numerics in the launch grid, it's like parallelized over on the SMs. But otherwise, within the Triton kernel, things are sequentially executed. So how it maps to Helion is that the outermost HL.tile is controlling the parallelization. But within the Helion, like that, for any of the inner HL.tile loops, for loops, it's sequentially executed. And sometimes if we want to write a kernel that's actually doing reduction on within the outer for loop, we need to do like atomic add across the SM so that the data stay consistent. Yeah.
Yeah, got it. Because like there's no concept of launch grid here, right? Like everything's a tile in your case, so you're even more tile pilled than Triton is itself.
Yeah. So in Helion, there's no launch grid concept, but when we lower to Triton, we do have it. So it's like uh sort of like abstraction leaking, but maybe with like other like other backends in the future, if there is like a different, but yeah.
We also do have an HL.grid thing where you can say for like program ID in HL.grid, which exposes the lower level concept of the lunch grid. Although we'd encourage people to use HL.tile because it gives the autotuner a lot more choices, and so you're sort of like locking the autotuner in to one choice if you manually specify the grid.
Oh, interesting. I see. So and how does composability work here? Like, for instance, like let's say, this is gonna sound like a meme, but just to sort of just humor me for a second, which is like you have a Triton kernel, and then you're like calling that from within a PyTorch program that like also like has like a Helion kernel interspersed. Well, how does this all work together, really? I mean, I guess there's just keep them separate, probably. There's no real reason to do this. The concrete use case. Oh,
Yeah.
sorry, go ahead.
Yeah, so Helion has the invariant that like one Helion kernel is exactly one CUDA kernel. Triton has the invariant that one Triton kernel is exactly one CUDA kernel. And so you can have like a PyTorch program with some Helion kernels and some Triton kernels and some PyTorch kernels and or whatever language you want, and they should all just compose together because they're all just separate kernels and they don't really actually interact. Except for their inputs and outputs.
Also, like something that we didn't mention earlier was Helion also already has a composability support with torch compile. So like if you have some model that you torch compile, and then you have your custom kernels in there, you can also have your custom Triton kernels. Now you can also have your custom Helion kernels. Currently, we just compile your Helion kernel down to a Triton kernel, and then we just send it along, similar to how we deal with custom ops using Triton kernels or even the raw Triton kernels. In the future, we are thinking about building more like a prolog or epilogue fusion inside Torch compile with Helion kernels. Like it is something in our roadmap, but we haven't gotten there yet.
So speaking of like when I was like looking at the output code, it was like giving me flashbacks to regular Torch compile output code. Is that like difference like is this because there's like a common tech stack, or this is just like compiler generated code will look compiler generated basically, and that's it?
It's because Helion uses Torch Inductor, and Torch Inductor is the backend for Torch compile. So there's a lot of shared code in the Triton generation.
Do you mind talking a bit more about that? Like specifically, like what does that really mean, and what does that look like in practice? I forget if you already mentioned this in your big architecture diagram, but I'd love to hear a bit more detail.
Yeah. So in Helion, like we don't have a massive library of Helion operations, and the reason why we don't need a massive library of Helion operations is you can use just regular PyTorch code inside your Helion kernel. So rather than having like an hl.exp, you can just call torch.exp. If you want to do and you can also call like more complicated things, like you can call torch.softmax inside your Helion kernel, and we know because we're using Torch Inductor, we can sort of lower that softmax into a output Triton code. And so most sort of pointwise and reduction PyTorch operations are supported. And the way they're supported is by going through the same tech stack that Torch compile uses. And so because we're using sort of that same tech stack, the output code will have a lot of sort of similarities. And it also is like what makes Helion able to sort of ingest PyTorch operations as its sort of main way of handling sort of that long tail of ops.
But concretely, the reuse is for like ops, right? It's like you have PyTorch ops. Yeah.
It's op level reuse. So we are not so Torch compile includes a lot of stuff that's like fusion, basically trying to decide, should I fuse X and Y? Should I fuse Y and Z? Should and like because Helion kernels like definitionally are just one kernel, like there's no fusion decision.
You sidestep the problem, yeah.
Everything's just one. And so we don't reuse any of the like graph level fusion decision code from torch compile, but for everything that's sort of op level, we reuse.
Yeah, like the philosophy like one we have is that like for the kernel authors to think about what dimensions to be parallelized, what dimensions need to be sequentially executed, and then write operations in PyTorch, in PyTorch syntax. So that's like the ideal that we are going for. Yeah.
Very cool. All right. I don't think I see any more questions in chat. So thank you for coming on, guys. If you have like any last words you'd like to say, or I think you guys mentioned that you're going to be doing a release on Tuesday, Wednesday. I think I wasn't sure if I heard correctly.
Yeah, so we'll be doing a beta release on Monday, and then during the Triton conference on Tuesday, Jason will be giving a talk. Or during the PyTorch conference on Thursday next week, Jason will be giving another talk. And Wednesday, we have right after the keynote at 10:30 a.m. PST, we have a Meet the Torch Compile and Helion developer session. And all three of us will be at that session. So feel free to come over and ask us any questions you have. All this information, like the conference details, everything can be found on our GitHub page. I think at the top of the README, there's like a plug like explaining like where you can meet us and all that stuff. And I guess to add on the GP Mod Discord, we have a Slack channel. Feel free to also reach us out there.
All right, wonderful.
Thanks
Jason, sorry.
and thanks for hosting. It was a lot of fun.
Yep. Thank you,
Cool.
Mark.
Thank you, Jason. Thank you all.
Thank you.
Thank you all for coming. Appreciate it, guys. Thank you so much.
Thank you.